There's a few more people still trickling in, so I'm just going to wait another 2 minutes before starting. In the meantime, maybe I can ask if anyone that's connected right now has any leftover questions from the previous lecture. Go ahead and raise your hand or just speak up if there's anything that you wanted to ask from the previous lecture.
Excuse me. Can you tell me where the recording for the previous lecture is? Because I missed the first one.
You have access to the Indico page for the course.
Yes.
So there should be a link attached to the first lecture in Indico to the recording. Do you see it?
Hold on.
Sometimes you have to relive the Indico.
And I see I'm on the overview page. There's a timetable page. Oh, okay, I see it. Okay, thank you. All right.
All right. Well, the numbers seem to have stabilized, so I think we can go ahead and get started. I have just a couple of housekeeping items before we start with the content of the second lecture. So the first is related to what we were just discussing. So both lecture notes, so the slides, as well as the Zoom recording will be posted on that main Indico page for the course after the lecture ends. I need a few minutes to annotate for myself where I left off with the slides, and then I'll try to do that right after the lecture. I'm just using the cloud Zoom recordings, which expire after 4 months, I'm told. So I will find a place to export these, which is more permanent. I mean, 4 months should give us time for the course, but I don't think there's any reason that they should all get nuked after that. So I'm looking into where the best place for me to share these recordings is, and I'll let you know when I managed it. Problem sets, especially for those of you taking the course for credit. I'm going to post problem set 1 tomorrow because it uses some of the concepts that we're going to use in today's lecture. And then the idea is that it would be due 1 week after that. For turning in the problem sets, what I would like you guys to do is to scan in or photograph your solutions. You'll probably want to work with pencil and paper, but scan in or photograph your solutions, and then I will use this program called Nifty, which allows you to send your scanned in problem set to my private Dropbox. And I'll include instructions on the form of the problem set itself for how to do that. What are we going to do today? Today, I wanted to recap where we sit in the sort of history of particle physics at the beginning of the 1930s or so. Then I'll continue on to talk about the neutron, the positron, and a rather complex story about pions and muons, which took a decade or more in order to completely figure out. So that will be probably the main content of the second half of this lecture. So just to remind you where we ended off last time, this is a slide about sort of the state of play in particle physics around the end of the 1920s, the beginning of the 1930s. And we said that this is a list of statements that most particle physicists at that time would have been willing to sign on to. So the atomic theory is well accepted. Matter consists of atoms. Atoms are known to consist of electrons and nuclei. The existence of the nuclei from Rutherford's experiments with scattering of alpha particles. The electronic structure of the elements, so basically chemistry, is described by quantum mechanics, and there's a lot of progress in these decades on refining the predictions of quantum mechanics and making them ever more precise. We believe that the nucleus consists of A protons and A minus Z electrons, which results in a net charge of Z on the nucleus. Electrons and protons have half integer spin. At least this terminology, spin, is coming into use around this time. They would go on to be called fermions. We've observed different kinds of particles interacting with matter in experiments. Some of those are deuterons, deuterium nuclei. So this would be 1 proton and 1 neutron in modern language bound together, and alpha particles, which are 2 protons and 2 neutrons, or helium nuclei. They have integer spin and they would be called bosons. And finally, we've observed also, in addition to charged particles flying through our chambers, we've also observed electrically neutral radiation, like X-rays and gamma rays, whose interaction with matter can be seen, for example, via the Compton effect. And this is understood to be electromagnetic radiation. So this is a relatively complete picture, which is about to be complicated by a couple of different discoveries. So the first of those discoveries is a picture that you see here. So what we have is this is an experiment by Curie and Joliot. They have a beryllium target and a polonium alpha source. So they point the polonium at the beryllium, and then they expose the radiations which are coming out of this arrangement. So you imagine whatever comes out of the beryllium target is entering this chamber from the bottom. And then they put a layer of paraffin. So this has a chemical formula, which is roughly something like C31H64. So it's mostly carbon by weight, but it's mostly hydrogen by number of atoms, and the hydrogen atoms are taking up most of the space inside, if you will. So what we see here is that this interaction between the polonium alpha source and the beryllium target creates some kind of neutral radiation. How we know it's neutral is by looking in this chamber. We don't see any tracks entering the chamber from the bottom. Right? There's some kind of bracket here, which is being used to hold the paraffin sample. But then once these apparently neutral rays impact the paraffin, we have a, at first, extremely heavily ionizing track, which pops out. And by this point, people are fairly adept at computing what the momentum of particles must be from how heavy of an ionization track they leave in the chamber. And using this method, the energy, or the momentum rather, of this recoiling particle here is calculated to be about 5 MeV under the assumption that this is a proton. So they know that this paraffin is a good source of hydrogen atoms. The nucleus of hydrogen, of course, is just a single proton. And so the hypothesis is that whatever neutral radiation is entering the chamber from the bottom is undergoing a scattering from a proton that is a hydrogen nucleus inside the paraffin. And then that proton is kicked out of the paraffin and proceeds to lose energy by ionization in traveling through the chamber. So this is a bit of a puzzle at the time. And the reason for the puzzle has to do with this energy of 5 MeV. So people are used to thinking of neutral radiation as being electromagnetic radiation, photons, where basically their energy is equal to their momentum because they have 0 rest mass. But if you try to calculate that momentum transfer of the scattering, that would be necessary to produce a 5 MeV proton coming out of this paraffin. You can use that information then to solve for what the energy of the incident gamma ray, which so far that's the neutral radiation which is known, right? Our photons, X-rays, and gamma rays. You solve for the energy of the photon, you get 50 MeV, right? It has to have a higher energy than the proton in order to accelerate this massive proton up to 5 MeV. And no one has ever observed a 50 MeV gamma ray before. Certainly, they don't expect this arrangement of a polonium alpha source and a beryllium target to produce such high energy gamma rays. That would be a higher energy gamma ray than has ever been seen. And so it presents a bit of a puzzle, and it is a guy named Chadwick, James Chadwick, who supplies the explanation. So some of you guys are PhD students or have been to graduate school, but I'm willing to bet that none of us had the same kind of experience in graduate school that Chadwick had. He was an Englishman, and he decided in 1913 that he wanted to better his knowledge of experimental physics. And so he decided to go to graduate school in Berlin, 1913, to study with Geiger. So he goes there, and then almost immediately after he arrives in the fall of 1914, World War I breaks out. And of course, Germany and the UK are on opposite sides of this war. So as a UK national, he is interned in a prison camp for 4 years until 1918. The prison guards were nice to this guy. They let him do some experiments in radioactivity and chemistry in a lab that was set up in the stables of the prison camp. But needless to say, his graduation was delayed by this time being interned. And it wasn't until 1921, so 8 years after he originally set out to do the PhD, that he managed to complete it back in the UK at Cavendish Lab in 1921. So he'd been working in the field for a few years by the time that these pictures of the highly energetic protons coming out of paraffin were shown around, and he set his mind to coming up with an explanation. So the basic issue, if you want to produce a 5 MeV proton from scattering gamma rays, is sort of akin to doing the experiment, and perhaps you've done in an early mechanics class. Let's say that you have a bowling ball on the table. You want to accelerate this bowling ball. If you have only light particles to throw at it, for example, ping pong balls, what you'll see is that in any given interaction, the ping pong ball will be reflected back with almost the same momentum from each of these scattering events, and will impart very little momentum to the bowling ball. So this is kind of trying to generate some intuition as to why these 5 MeV protons are unlikely to be produced by electromagnetic radiation. As we said a couple slides ago, you would need a really large energy of the gamma coming in order to produce a recoil of a proton of 5 MeV, in this case, 50 MeV. And Chadwick had the following insight. What if instead there is a neutral particle whose mass is similar to that of the proton? Then you don't need this high energy of 50 MeV in order to eject a proton. What you would imagine then, if these two particles have roughly the same mass, is that the neutral version just hits the proton. It's like rolling a bowling ball at a bowling ball, right? The first one can come to rest, and the second one will basically pick up all of its momentum and roll away. You'll do this as one of the homework problems. And so Chadwick, based on this argument, hypothesized the existence of a neutral particle with the same mass as the proton, called the neutron. And the obvious explanation of this phenomenon in terms of the neutron led people to accept the existence of the neutron. This also helped to get rid of some other problems with the picture that we had in 1930. So as I mentioned on slide 2, in order to explain why the mass of the nucleus was more than the charge of the nucleus, people assumed that there were electrons bound up in the nucleus that partially canceled the charge of the nucleus. But people weren't really able to explain the phenomena of like isotopes that way. Like, what is the reason that some elements seem to always have the same number of electrons, if you will, in the nucleus, whereas other elements have a sort of spectrum of different isotopes? It's unclear why it's not so easy to transmute one isotope into another by like bombarding the nucleus with electrons, right? If you thought that what was going on is that electrons were captured by the nucleus and then that cancels out the charge, it would suggest that there's probably should be a higher capture cross-section, for example, for electrons on the nucleus than what's really observed. It's very hard, actually. There are such phenomena, but it's very hard to turn one isotope into another by putting electrons into a sample of material. So this hypothesis of the neutron is sort of rapidly accepted because it gives the whole idea of like radiochemistry a much simpler basis. Another thing which was going on at this time around 1930 is that people were making progress on a relativistic form of quantum mechanics. One of those people was Paul Dirac. He published his first paper about what would come to be called the Dirac equation in 1928. And the business that he's engaged in here is trying to write a relativistic wave equation for the electron, also incorporating the sort of then new concept of spin, which he needs because experimentalists had started to observe the Zeeman effect. Does anyone in the audience remember what is the Zeeman effect? Can you tell me what the Zeeman effect is? Has to do with spectroscopy of elements. What happens if I immerse an element with a well-known spectrum in a strong magnetic field? What will I see?
That's when you split the energy levels, right?
Exactly. So before the concept of spin, people couldn't really understand why, when you immerse an element with a known spectrum in a strong magnetic field, what you observe is basically a doubling of the spectral lines, or at least some of them. The single line splits. And in the modern vocabulary, what we would say is that, some of the electron spins are aligned with the magnetic field versus anti-aligned with the magnetic field. There's a different amount of energy associated with those two states. And so as a result, the spectral lines split from one line into two in a strong magnetic field. This is used now experimentally, for example, to measure magnetic fields just by looking at the spectrum, for example, of a distant star. One can infer how strong the magnetic fields there are by the degree of splitting that happens by the Zeeman effect. Anyways, people didn't understand any of this at the time. And so one of Dirac's projects was to write down an equation for the electron, which incorporated this concept of spin and also respected special relativity. The sort of critical physical question for an experimentalist in any quantum theory that you might write down is like, what are the physically observable quantities defined by the theory? And Dirac's equation has two sets of solutions: positive energy eigenvalues and negative energy eigenvalues. So people were sort of thinking about to what extent the negative energy eigenvalues of the equation should be taken seriously as a physical prediction versus a mathematical artifact. The negative energy solutions not only exist and satisfy the equation, but actually, even if you start with a positive energy state and then allow it to evolve in time, eventually you pick up components of this negative energy state. So Dirac thinks that the negative energy states should be taken seriously because they're necessary in order to explain the time evolution of even a physical system that starts out with a positive energy. His first idea is rather clever and actually sort of corresponds qualitatively to some concepts that we use even in modern condensed matter physics. His original idea was that these negative energy solutions are the holes, to use modern parlance, in like a material. So you have a bound state of electrons in a material. You take away electrons, you produce holes, like positively charged remnants or the absence of electrons. And you can track those through the lattice of a crystal, for example, using quantum mechanics, similar to what would be for the actual physical electron propagating through. So Dirac at first tried to argue that these negative energy solutions are the holes, which would basically amount to an excess of protons relative to electrons in the material. In fact, he went so far as to propose originally that the negative energy solutions are the proton. But feedback from Oppenheimer and Weil convinced him that this could not be the explanation based on some quantitative comparisons with the known behavior of the hydrogen atom and essentially on the mass difference between the proton and the electron. Like, these negative energy states still have the mass of an electron, whereas we know the proton mass is some 2,000 times larger than the mass of the electron. So in 1931, Dirac wrote a follow-up paper proposing what he called at the time the anti-electron, so that these negative energy solutions correspond to a real physical particle, which is the antimatter conjugate of the electron, which later people would call the positron. I think this is arguably the first successful prediction of a particle in this field. It would be shortly followed up by confirmation by pictures like the one on this slide. So this is a picture from Anderson's lab at Caltech. This picture was published in 1933, so a couple of years after Dirac's follow-up paper arguing that the negative energy solutions of his relativistic wave equation for electrons should be taken seriously as an antimatter counterpart to the electron. So what we have here is a cloud chamber photograph. This cloud chamber is immersed in a magnetic field, as we discussed last time. Here, this is a field of 15 kilogauss, which is pointing into the plane of the screen as this picture is taken. One problem that people had in interpreting the results of these experiments is that it was hard sometimes to infer what the direction of a particle propagating through the material was. If you remember back to the previous lecture, we had pictures, for example, of alpha particles losing energy in traversing the gas of the chamber. And there you could sometimes tell like where the end of the track was, because you would have these regions towards the end of the track where the particle is basically ranging out, and it kind of goes on this little random walk at the end, deposits a lot of its energy there. We talked about the Bragg peak. When looking at especially lighter particles interacting, it's not always so easy to read directly off the photograph what the direction of propagation of the particle is. And so what experimenters began to do was to instrument their chambers with plates. The advantage of this plate is that the particle should lose energy passing through the plate. So can somebody tell me, based on this photograph, what direction the particle, this main track in the middle, what direction this particle is traveling by reference to the lead plate? Scott says it's going upwards. Scott, can you tell us how you know that?
Oh, hi. Yes, I'm having some microphone problems. It's going upwards because the curvature is higher above, which is, has less momentum above, so it lost energy.
Exactly right. And one can even do quantitative computations of how much energy is lost by fitting a circle basically to the length of track just after it emerges from the plate versus the length of track just before it enters the plate. And you can make a quantitative comparison then. People by this point had done experiments with beams of electrons, and they had, this beta theory of how much energy electrons should lose per unit length. So the beta theory is known to be correct, and that means for a plate of a given thickness made of a given material, one can actually calculate pretty exactly, this plate is thick in terms of like number of individual interactions happening. So the statistical uncertainty in the energy loss is actually rather small here. One can calculate quantitatively exactly how much energy an electron, for example, would lose going through this plate versus an alpha particle. And what you find is that if you do that calculation for this picture, the dEdx of this unknown particle going through the plate is consistent with an electron. It loses the same amount of energy going through the plate that an electron would, except the curvature is in the opposite direction that we would expect for a negatively charged electron. So this thing appears to be just like an electron, except it has a positive charge. And this is interpreted as proof positive that Dirac's theory is correct, that the negative energy solutions of the Dirac equation are not just a mathematical artifact, but that in fact, They correspond to a real physical particle. Because it's positively charged, people call it the positron, and we now know that their interpretation was correct. The positron is the antimatter equivalent of the electron. This is written up in a rather famous short paper called The Positive Electron by Anderson in 1933. Here he says, out of a group of 1,300 photographs of cosmic ray tracks in a vertical Wilson chamber, 15 tracks were of positive particles which could not have a mass as great as that of the proton. Again, we know that by calculating the energy loss that a proton would experience in the lead plate and contrasting what the energy loss expected from an electron. From an examination of the energy loss and ionization produced, it is concluded that the charge is less than twice and is probably exactly equal to that of the proton. If these particles carry unit positive charge, the curvatures and ionizations produced require the mass to be less than 20 times the electron mass. These particles will be called positrons. Because they occur in groups associated with other tracks, it is concluded that they must be secondary particles ejected from atomic nuclei. That last comment, I think we would no longer agreement with, but the rest of it is spot on. He is, of course, in dialogue with the other things going on in particle physics at the time. So he's aware of, for example, Chadwick's theory of the neutron. And he has this comment later in the paper, which is an interesting theory. It turns out not to be true, but he says, if the neutron should prove to be a fundamental particle of a new kind, rather than a proton and negatron, that is electron, in close combination, the above hypothesis will have to be abandoned, for the proton will then in all probability be represented as a complex particle consisting of a neutron and a positron. So they really have a hard time letting go of this idea that the nucleus somehow involves either electrons or positrons to like either augment or subtract from the charge. Of course, I think from the modern view that the correct answer is simpler. They're a neutron and a proton, and while they are composite particles, they're not composites of each other with a negatron or a positron. They're just two different charge states of well, we'll get to the composition of neutrons and protons later in the course. Around this same time, in Japan, famous theoretician Yukawa is trying to make some calculations about what force is likely to hold the nucleus together. So we now have this picture of a nucleus which is made up of protons and neutrons. Perhaps they're composite particles. Even if there's some negatively charged components running around in there, we do know that the overall charge of the nucleus is overwhelmingly positive. And so Yukawa is trying to investigate what must be the nature of the force that holds this thing together, despite the fact that it has a large net positive charge. And he figures that this force must only work at relatively small distances. And the reason he thinks so is that, atoms remain separate from one another. There are such interactions where like a nucleus absorbs an alpha particle and changes into a different kind of nucleus, but we need very large energies in order to overcome the Coulomb repulsion and get that thing in there. At sort of normal room temperatures, there's no real possibility for nuclei to just collide and combine like that. And so he hypothesizes that there's a very strong, in terms of its interaction strength, force, but with a short range, shorter than the range of the Coulomb potential. Otherwise, the relative strength of the two would remain constant throughout space. So he takes something which is sort of inspired by the Coulomb potential, and then he adds this additional exponential decay term to it. So instead of a 1 in the numerator, we have e to the minus lambda r, where lambda is a characteristic distance, which is about the size of the nucleus. Lambda would be like 1 over the size of the nucleus in these units. You'll do this problem on the homework to figure out how energetic the force carrier particles would be in order to have a range on the order of the size of the nucleus. But spoiler alert, the answer is about 100 MeV. So the nucleus has a size of about 1 femtometer or 1 Fermi, we would say. And that implies that the force carrier has a mass of about 100 MeV. So the idea that there should be some new particles with a mass of 100 MeV, this is kind of, in logarithmic terms, in between the electron and the proton. That idea is kind of in the air because of Yukawa's prediction, and it's going to combine with some data from cosmic rays. Unfortunately, as we said earlier, typically the particles coming from nuclear decays are sort of order 1 to 10 MeV. Nobody knows of any nucleus which gives out rays of 100 MeV, much less multiples of 100 MeV that you would need in order to produce this particle in interactions with a target nucleus, for example, at rest. So people are questioning if there is a new particle about 100 MeV, I'm not going to find it in nuclear decays or in nuclear interactions. So what can I use as my source instead? And the answer has to do with the same topic that we talked a little bit about last time in terms of identifying the neutral and charged components, and that is cosmic rays. This is a artist's rendition of what a cosmic ray shower initiated in the very high atmosphere sort of looks like as it shoots down towards the surface of the Earth. This comes from the Auger Observatory, where they have a large air shower array spread out over a big area of land, and they can use that to reconstruct the direction and energies of the very highest energy cosmic rays impacting the Earth. And for most of the rest of what we're going to talk about today, cosmic rays are really the source of high energy particles. Anytime we're going to talk about anything more than, say, 10 MeV before the advent of the accelerator, the only source in nature for such energetic particles is cosmic rays. People still do physics with cosmic rays, as evidenced by the fact that this Auger experiment is still going. And that's because cosmic rays, even relative to accelerators, still have some advantages. Obviously, they produce energies which are much higher than what are accessible from nuclear interactions. We just said that. They also still produce energies higher than even the highest energy accelerator. So the LHC right now is the most powerful accelerator that humans have ever built. And yet we routinely see cosmic rays with many orders of magnitude higher energy than even the LHC can produce. They have a mix of particle types. So if one builds an experiment which is capable of distinguishing between the different particles, they have the advantage that you can kind of study the whole zoo of particles using the same facility. Whereas in a colliding or an accelerator-based experiment, you're typically going to be considering just a single type of particle as an initial state. Of course, that can also be a disadvantage, right? The need to disentangle the different components of the cosmic ray, charged versus neutral, positive versus negatively charged. As we'll see, there's particles of different masses mixed up in there together, means that there's some work required by the experimenter to figure out what all is in there. Another disadvantage of cosmic rays for doing physics is that they're asynchronous, both in time and in place. So when I build a particle accelerator, I usually, as a result of the acceleration technology, have sharp, at the very least, I can turn my accelerator off and then back on and observe different rates of background versus signal in my experiment. There's no way to turn off cosmic rays. There's no way to predict where the next cosmic ray will come. There's no time structure to it, and they kind of irradiate the whole Earth more or less isotropically, modulo the considerations about magnetic field strength of the Earth that we talked about last time. The rate is strongly energy dependent. So while they produce some very, very high energy particles, those rates are very low. And they're to be contrasted with a very high rate of lower energy particles that your experiment needs to be able to distinguish from. And finally, the atmosphere itself is a medium, it's material that the particles in cosmic rays can interact with. So the atmosphere absorbs energy from cosmic ray particles. And this limits, for example, if you're sitting on the ground, which cosmic rays can actually enter your experiment, because some of them are simply absorbed by the atmosphere before they have a chance to get to your experiment. So what are cosmic rays? This is a modern understanding. People working in the 30s wouldn't have understood this, but what we now know is that these are highly accelerated nuclei, which fly through interstellar and indeed even intergalactic space on their way to the Earth. So this shows different elements and their relative abundances in the cosmic rays. So by far the most common, with a relative abundance of 550 on this chart, are hydrogen nuclei. It's basically just a proton. It is just a proton. But there is also significant components from helium. So these would be basically alpha particles. Lighter elements like carbon through oxygen have a significant component. And if you go up to much heavier elements, even as heavy as iron and nickel, there is a measurable, although small fraction of cosmic rays, which are these heavier elements. Does anyone know like what out there in intergalactic space is actually generating these very energetic nuclei? Where do they come from? Anybody know?
Quasars, or
Quasars are one source. Yeah. Do you know any others? So I should say this is like an active field of study. People are still building big cosmic ray detectors and then trying to do astronomy with them in order to identify where they come from. One thing that we know most likely is that a lot of them come from supernovae. So these could be supernovae. Yes, exactly. Supernovae. So they could be supernovae in our galaxy, but also there's probably a background of supernovae in faraway galaxies. The magnetic fields in the intergalactic medium is very weak. And so charged particles can propagate for a really long distance, intergalactic distances, before they might eventually enter our galaxy. We think probably the majority of them, especially at lower energies, come from supernovae. But then, yeah, as we go up the energy spectrum, we think that there are contributions from the active galactic nuclei of other galaxies, right? So in the galaxy, in a nucleus of a galaxy, there's a really super heavy black hole. And particles falling into that black hole attain relativistic velocities. And then there's all kinds of interactions with the electromagnetic fields around these objects. You basically picture this plasma swirling around a black hole and particles within that plasma interacting with each other. Sometimes one of them will receive a big kick of energy and fly out towards a neighboring galaxy. Quasars, Pierce already mentioned as a possibility. So this is like a super fast spinning object that has really strong electromagnetic fields around it. Particles can get trapped along those field lines and undergo acceleration by sort of looping around inside of those changing magnetic fields, and eventually some of them can receive enough energy that they fly away. Gamma ray bursts, we know that there are sources of extremely high energy gamma rays out there. This probably has to do with some kind of you have a lot of energy stored up in electromagnetic fields of like rapidly spinning objects, and then like the field geometry can rapidly change, leading to a huge burst of energy, which is released in the electromagnetic spectrum. This can then through like Compton type events, import high momenta to other charged particles, which might be around, for example, in a supernova remnant or whatever. But this is still an active area of research. This is a picture of the composition of cosmic rays in terms of different species of particles. And what you see here is that different types of particles have different characteristic energy spectra. So there's a couple interesting things to look at on this plot. The first is that protons and neutrons, which we think the actual primary cosmic rays, initiating the showers in the upper atmosphere, are largely made of protons, but can also be these heavier nuclei. This distribution has basically just a falling spectrum. The higher you go in the atmosphere, the more flux you observe. But for muons, for example, or pions, we actually see something different, which is a curve that has a turn on, right? At the very outer reaches of the atmosphere, those have relatively lower components of the flux, whereas when we go closer to the surface, that is at a greater depth into the atmosphere or a lower altitude in kilometers, these make up a larger and larger fraction of what's reaching us. Can somebody explain why there are relatively few muons at the top of the atmosphere, but they actually dominate the flux down by us? What's the reason for that?
Well, I'm not sure exact. Oh, there's a raised hand. Never mind. I see that.
John, why don't you take a crack at it first?
Cosmic ray muons are secondary particles. They're produced by cosmic ray interactions.
And then why do they come to dominate as we get closer to the surface? Why don't they also fall off as we go deeper into the atmosphere?
They have some of the highest penetrating power, or I guess their interactions they interact very little with the surrounding atmosphere, so they can make it to the surface.
Exactly. Just like in CMS, how only the muons or only mostly muons can penetrate through all the layers of shielding of the muon system. That's essentially what the atmosphere of the Earth does. Since muons are interacting relatively weakly with that material compared to, for example, electrons, which you see here are many orders of magnitude less. They tend to penetrate all that material of the atmosphere and get to the surface. Another interesting plot is here. So this is showing, it's kind of complicated. This is on the y-axis, we have the momentum spectrum of the muons. And we have basically the angular dependence of the, so we have the momentum spectrum of the muons on the x-axis here, and then on the y-axis, we have essentially the flux of muons, the momentum-weighted flux of muons reaching the surface. And then we have that curve drawn for a couple of different angles. We have theta equals 0, meaning that they're coming basically straight down, perpendicular to the surface of the Earth. And we have points on that from like a few different measurements. And then we have a corresponding curve for theta equals 75 degrees. So this would be like sort of making a low angle with the horizon of only about 25 degrees. So what we see is that for 75 degrees, the momentum spectrum is much harder. Or putting it another way, for a given momentum, let's pick, 7 GeV, which should be something like here. There are many more muons coming from straight above us than at an angle. So can somebody explain why the momentum spectrum is different as a function of angle? Why are the muons that reach us from an angle of 75 degrees so much harder in their PT spectrum than muons coming straight down? This has to do with relativistic kinematics. Can somebody explain it? Are muons stable? John, go ahead.
So because the muons decay, the muons with the higher boost, or so if it has a larger angle, then it has a higher travel path. So when
Mhm.
muons decay, they need to have a higher boost in order to increase their lifetime to make it with the longer travel path.
Exactly. So for a lower angle, the interaction of the primary cosmic ray with the top of the upper atmosphere is much further away from us in terms of number of kilometers away from us. And so in order to reach us, the muon, which has a finite lifetime, has to be boosted to a much higher momentum to reach us along that much longer path before decaying. So that's exactly the right description. This is a plot of, you notice that actually CMS is on this plot along with some other experiments of different kinds, including some neutrino experiments and other collider detectors. This is showing what's called the muon charge ratio. So the number of positive over the number of negative muons, which is always above 1 and also has some PT dependence. The reason why we see more positively charged muons relative to negatively charged muons has to do with the charge of the initial particles initiating the shower. All those atomic nuclei we saw in the chart a couple of slides ago, those are all matter. So the protons are positively charged. That means that all else being equal, there's going to be an excess of positively charged particles in the shower because of charge conservation. And this is something that CMS, for example, was able to measure while it sat on the surface before being lowered into the cavern. One last one last plot about the history or the physics of cosmic rays is this one, which shows what we think is the overall energy spectrum of cosmic rays reaching us. You can see there's a generally falling distribution in terms of energy, as we would expect, right? The more energetic events are probably rarer because you need to rely on ever more improbable momenta transfer in these active galactic nuclei, supernovae, whatever. There's some structure here, what's called the knee, the second knee, and the ankle. That has to do with different, there's some, albeit weak, there are some magnetic fields in interstellar space, and then also the different sources of cosmic rays, each are generating things with their own spectrum. So the interplay between these two things does some sculpting of the falling spectrum so that it's not exactly just like a simple power law or anything like that. What I want you to notice from this plot is this line that I've drawn in here called the GZK cutoff, after which the spectrum of cosmic rays falls off really rapidly. And the reason for this fall off is that at these extremely high energies, so we're talking about close to 10 to the 20th electron volts, the interaction probability with individual atoms and even with electromagnetic fields in the intergalactic medium starts to blow up. And so the universe, below this cutoff, the universe is relatively transparent to cosmic rays, but above this cutoff, the intergalactic medium starts to become opaque to cosmic rays. So presumably more of these are produced, but they just simply never reach us because they are more likely to interact with stuff in the way. If you make this as a function of angular distribution in the sky, try to do astronomy with it, you'll see that there's actually a slight deficit of these highest energy cosmic rays from the direction of our own galactic center. So while some high energy cosmic rays presumably come from our galactic center, more of them apparently are absorbed than are created. And that means that a significant component of the very highest energy cosmic rays are indeed coming to us from outside the galaxy, which corroborates the existence of this GZK cutoff. Anyways, going back to our initial picture here, the momentum of this particle, as we said before, is measured with this analyzing magnet, 15 kilogauss, pointing into the page. And what Anderson and his compatriots start to do is to sort of total up lots of events of this type. As I mentioned before, people eventually event chambers which automatically expand every so often and automatically trigger the photograph to be taken. And this lets you start to build up statistics of different types of particle interactions. You can then sort of the mass analysis of the change of momentum of these particles when they pass through the lead plate, as well as their charge. And you can start to build up histograms of how different types of particles interact. So you can see here one of the themes that I mentioned back in the first lecture of the course is the transition from like doing analysis by image only to doing analysis by statistical methods. And here you see a very early form of that transition beginning to take place. What Anderson and his colleagues notice is that if you plot the energy loss, this would be dE dx in modern parlance on the vertical thing here, and then versus the energy of the particle itself as calculated from the curvature. So this vertical thing comes from how much the curvature changes going through the plate, and this x-axis comes from just what the initial curvature is. If you make a scatter plot, you can see that there's basically at least two populations of particles here. So the first distinction is whether or not there's a shower present. I'll talk more about showers in a minute. But even if we ignore those shower particles for a moment, we can see a clear difference between what he calls single particles and what he calls shower particles. These shower particles, the open circles, tend to go along this line where the energy loss is very highly correlated with the energy, versus this other population, the dots that he calls single particles, where the energy loss is, first of all, much less than the open circles, but also doesn't seem to be very well correlated at all with the momentum or energy of the particles in MEV. So shower particles are observed in coincidence with other high energy particles. That is, you see more than one track in the picture, and they have energy loss consistent with the beta formula that we had before for energy loss by electrons, right? There's this figure of merit x naught, the radiation length that you can calculate. And these particles along this diagonal basically are consistent with the hypothesis that they're electrons or electron-like. Single particles are observed mostly by themselves, not in coincidence with other particles, and they have basically zero energy loss. So the energy loss of the single particles is inconsistent with electrons. Plus, if electrons had such high energy, like 500 MeV, they would often induce a shower in the plate, whereas for the single particles, they don't produce showers. So this is a little bit of a confusion. Just as an aside, I'll say a few words about the development of electromagnetic showers in matter. Why do electrons tend to initiate showers as they go above a certain energy? So as we saw last time, one of the main ways that electrons lose energy by passing through a material is Bremsstrahlung. They are flying through the material. They make a close approach with the nucleus of an atom in the material that has a very strong electric field. Because the electron is so much less massive than the nucleus, very little momentum is exchanged in this interaction, but it does cause the electron to be deflected by that electric field. And as we know, when an electron undergoes, when any charged particle, but especially light ones like electrons undergo an acceleration, they emit radiation, and we call that radiation Bremsstrahlung. So what tends to happen in a material, if I'm above a certain energy scale, is that my electron will have a close encounter with the nucleus. It will be deflected, and it will emit a high energy photon. And then this photon can then undergo the interaction that we looked at in a cloud chamber photograph last time, which is pair production. And then as long as the particles in this developing shower still have enough energy, we can undergo successive rounds of this. So the electron, if it still has enough energy, can undergo successive rounds of Bremsstrahlung. The photons, if they have enough energy, will trade momentum again with the charged particles in the material and have a pair production take place. If these pairs then have enough energy, they can undergo their own Bremsstrahlung, et cetera, et cetera. And what we end up doing is building up what's called an electromagnetic shower from successive rounds of Bremsstrahlung and pair production. So this process goes along and along until we're below the threshold energy for pair production, which is basically MEV. And the rest of the energy is then lost by ionization of the material. This is called the Bethe-Heitler theory of electromagnetic showers. We'll see on the homework a problem to show that the total charge path length in the shower is proportional to the energy of the incoming particle. And indeed, this is the principle that underlies electromagnetic calorimetry, which we'll talk about later in the course. But what I'd like to talk about right now is how people were able to understand that this is what was going on. And the key technology for understanding this is called the Geiger-Müller counter, which was again invented around the same time, beginning of the 1930s. So Geiger counter has a couple of components. There's a positively charged anode wire running down the center of the tube. And then the tube wall, so this outer surface of metal on the inner wall of the tube is held at a high negative potential. And we're typically talking here about potentials on the order of 1 kilovolt, something like that. Geiger was a Rutherford student at Manchester, and then Mueller was Geiger's student, and their names both get on this device. It's cheap to produce. It's relatively portable. So as long as you have a power supply, you can carry this thing anywhere and measure the rate of ionizing radiation. It's self-contained. It doesn't need gas coming in or flowing out, just a potential to be applied. And it produces a nice clear peak in the current. So if I monitor the current between the inner wire and the outer surface, when a charged particle goes through, I'll see a clear peak. And even using analog electronics, that peak is relatively easy to process. We'll see some ways that people devise processing. What's happening on the microscopic level is that a particle of ionizing radiation comes in. There's a gas inside the tube. We choose the gas. Particular gases are better, some better than others, for their properties for filling this tube. But basically, we want a gas or gas mixture where once an initial ionization event occurs, so we have a high energy particle going through and knocks into an atom in the gas. It gives enough energy to that atom to liberate one of the electrons from the gas, ionization. And then that electron, as well as its corresponding positively charged ion, begin flying in opposite directions. So here we've pictured what happens with the electrons, but of course you could say a similar thing for the positively charged ions. They are also feel a pull, but in the opposite direction. And what we want to do is give the have a sufficient voltage here that actually this electron, in falling through the tube, gains enough energy that it can actually ionize successive rounds of gas molecules. So we create an electron positive ion pair here. The electron then falls through the electric field, gaining energy all the while until it has sufficient energy to ionize again. Then at each of these secondary ionization points, a positively charged ion flies out while the additional electrons continue to fall inward. And basically what you get here is a large multiplication of the original charge, which was just one electron. And you can end up, depending on the operating voltage and the gas that you choose, you can end up with a measurable pulse from thousands, millions, whatever, of electrons reaching your anode wire. So this is a good technology. We still use it in like radio protection today. Especially the early tubes, though, were rather noisy. And so people want to perform experiments where they can reliably distinguish real signals from ionizing particles from the noise. And they also have a relatively poor spatial resolution. This tube doesn't tell you anything about where inside the tube the event happened. So this is all sort of one electronics channel by modern standards. And so typically these are, sized sort of macroscopic objects of sort of size 10 centimeters or something like that. And so there's no real way to recover the spatial information about where inside the tube this thing happened. So if we have a particle detector, which is reliable in terms of creating a pulse when a charged particle goes through, but also very noisy, can somebody tell me an idea that we might have for how can I suppress the noise and enhance the signal from real particles going through this tube? What's an arrangement that would help me to reject the noise and enhance the signal from a detector technology like this? Any idea? What could I do if I had two tubes? Anybody?
I guess if you had two, you could try and look for coincidence.
Yeah, can you say more about that? What does it mean, coincidence?
You could try and look for the simultaneous like firing in both of the tubes.
Yeah, exactly. And how would that get rid of the noise and enhance the signal? Why does coincidence get rid of noise?
If we assume that the noise is purely random, then it's less likely that you have two noise events at the same time, versus if your efficiency is pretty high, you can expect that a true signal would have two events at the same time.
Yeah, very good. So this is the insight that was had by people around this same time. And what they started to do was to build up various geometric arrangements of multiple tubes and then connect them to coincidence circuits. This is a picture from Rossi's book, Cosmic Rays, from 1964. I really highly recommend this book, even though it has really nothing to say about like modern high energy physics, in the sense that he's writing before collider experiments and stuff. But I think it's an excellent window into sort of the mind of a physicist. And he writes in a very engaging, sort of highly readable matter. The whole book is basically about all the different puzzles that came out from cosmic rays and how they built up the instrumentation to resolve them. I think it's really one of the very best books on particle physics, even though the subject matter is a little old. Rossi was Italian by birth, but he was also a Jew. He was a professor at Padua in the 1930s, where under the pressure from Nazi Germany, Italy started to incorporate its own sort of like racial purity laws in the universities. And so he eventually lost his professorship because of his Jewish heritage. And then he started out on a journey around the world. He stopped in the UK. He eventually came to the US, where he contributed to the Manhattan Project at Los Alamos. And he settled into a professorship at MIT after the war, where he continued doing experiments in high energy physics. Anyways, you can learn more about this from his book. But this is a picture of one of the very early coincidence circuits to be used in high energy physics. So here we have three Geiger tubes, G1 through G3. Each of them is connected to ground through a resistor, and then also through these tubes T1 through T3. So these are vacuum triodes. That basically means that there is a central grid inside of the vacuum tube, which is represented by this dotted line. And then there's a positively charged end and a negatively charged end. And basically no current will flow here unless the grid becomes charged. When you charge this grid, it basically sucks electrons off of the negatively charged side and gets them flying towards the positively charged side, and current flows. So here you have some big resistor R, which is in series with your battery or power supply on the right-hand side of this plot. And what you do is you monitor the voltage at A. If one of these tubes discharges but not the other two, then all the voltage drop will basically be across R here, because there's no current flowing through these other two paths of the circuit. You obviously have to choose these resistor values in order to make this thing function best. But given suitable choices of resistors, you can arrange a situation where the voltage drop is basically across this resistor here, and not through any of the individual paths, but that if all three tubes fire at once, then there's a voltage drop mostly across these bottom resistors, and that means that the voltage at A will jump towards the positive battery voltage. And then you monitor this thing basically by attaching one of these, at the time they would use these paper tapes that would run through a recorder, and then you have a little pen which is deflected based on the voltage that you measure, for example, from A to the bottom of B here. And what you can see is that by monitoring like the individual tubes separately from this coincidence circuit, you can make a plot which only has pulses when a charged particle or charged particles in time with each other pass through all three tubes. And so this sort of arrangement allows you to reject most of the noise on the individual tubes. And it also unlocks the possibility to do different kinds of experiments by like taking G1, G2, and G3 and putting them in different spatial arrangements with like absorber or not in between them. There's all kinds of clever experiments you can now do to see which types of radiation penetrate through different kinds of arrangements of the tubes. One simple thing you can do is to image the so-called showering versus non-showering components. So if you put these three in a sort of triangular arrangement, there's no single particle which can ever pass through all three because of the geometry of the situation. But if you put this thing inside of a box made of some absorber, what you notice is that you do start to see coincidences of all three. And that's related to the fact that some component of the cosmic rays coming in is this so-called showering component. And when a shower happens, like in this lead, the shower particles can go through all three tubes at once and fire a coincidence. You can then do experiments where you basically vary the thickness of this lead and look for the coincidence in the three tubes as a function of the thickness. And what you'll find is that when you start with no lead, you observe very few showers, right? There's some chance that things will shower just in the air, but lead is so much more, so much heavier per unit length than air. It's much more efficient at developing these showers. And then up to a certain thickness, and that thickness is going to be related, of course, to the X naught of your material, you'll start to see more and more coincidences as the lead gets thicker. Then as the lead gets thicker yet, you see this thing start to turn over. And that's because now the lead is getting thick enough that at least the initial generations of shower particles are resorbed by the lead before they have a chance to meet your tubes. And if you want, this is kind of a very direct way of imaging the development and then decay away of these shower particles. So in the early generations of the shower, you're still building up more and more particles, more generations of the shower. And then as you get to the later generations, the energy per particle starts to fall away and they get absorbed back in the lead before you can see them in your tubes. So this is a very direct way of imaging this process of showering. If you want to take it a step further, then you can combine your coincidence counter with a cloud chamber. So in between your tubes, you can put the chamber here, C, and then you can have the either photography, like the flash for your photograph of this chamber, driven by the coincidence of these two tubes, or even the expansion of the chamber driven by the coincidence of these tubes, if it's not just constantly expanding and contracting. So here we start to combine, let's say, a triggering detector with like a higher bandwidth, but more costly to read out detector like the cloud chamber, sort of combining electronic logic with a photographic image. And this, I think you will find recognizable as sort of the genesis of the types of experiments that we do even today. We have some parts of the experiment where I optimized to deliver triggering signals in time and drive the readout of a more slow component, which we only want to do if we have reason to believe that there's some that there's something interesting inside the chamber here. And I think you can really see an experiment like CMS in this picture. This is from Blackett in 1933, triggering on a shower, which is passing through his magnetized chamber. You can then continue building up your technology with more layers of absorber, more coincidences, until you can observe images like this one. So this is a photograph of an electromagnetic shower in lots of detail. What you have here is a cloud chamber with many thin lead plates interspersed with the chamber holding the vapor. And then this whole thing is triggered by the Geiger counters sort of on either side of the picture here. And so what you get here is a really nice picture of the whole shower developing and then falling off, right? You have just a few incident particles on the left-hand side. You can see the shower generations multiplying, especially each time it passes through the lead. And then by the time you reach the later generations of the shower, the tracks become more sparse and the shower has essentially died out by the right-hand side here. Rossi called this the materialization of energy, which I think is a very cool phrase. Well, we would call it a calorimeter. The energy of the incoming particle is proportional to the total length of charge track in this picture. So what people started to do as they got more clever with these different geometric arrangements of things was to start interspersing tubes and chambers with absorbers. And what you observe is that there's a couple of different components. There's a component which looks very much like electrons, maybe positrons, that tends to range out in a few centimeters of material. And then there's what they call the penetrating component, what in Anderson's histogram above was called the single particle as opposed to the showering component. And basically what you find is that you can build long coincidences separated by many interaction lengths worth of lead, and some fraction of cosmic rays will still fire this thing. This was known as the penetrating component. And based on considerations of energy loss as a function of the incident particle mass, people had the idea that perhaps Yukawa's prediction of a particle of 100 MeV could be realized in an arrangement like this. If you have something which is kind of like electron-like, has the charge of an electron, but is much heavier, you would predict events of exactly this kind, right? Because it's going to lose energy much more slowly passing through the lead than an actual electron was. So could it be that the penetrating component of this thing is Yukawa's meson? That's the experiment that Street and Stevenson set out to do in 1937. They have 4 counters here, 1, 2, 3, and 4. The coincidence that they're looking for is 1 and 2 and 3 and not 4, right? So by inverting the logic, you can also exclude things from the coincidence, and we would call that a veto in today's experiments. So we're looking for the coincidence of 1, 2, 3, and then we veto on 4. And then we have a chamber in here, which you can then image. So what they wanted to do here was to try to catch a penetrating track, which is got sufficient energy to pass through 1, 2, and 3, and then will range out in this absorber, which is labeled C here. They apply a pretty high field here, 3.5 kilogauss, and that's because they want to sweep away, for example, lower energy stuff, which is in the which is coming about, for example, from a shower passing through all this, and they really want to zero in on the possibility of one individual particle which penetrates enough to go through this chamber and through 3, but then ranges out in C before going to 4. And this is a picture of their cloud chamber photograph. This is like an extreme close-up of the chamber. And the reason that they're taking it with such a high level of magnification is they want to carefully count how many nucleation sites there are, and they can convert this count into the DEDX for the particle. If they know the density of the vapor in their chamber and they know the actual amount of energy lost, then they can compute what the mass of the particle is. And so from pictures like this, they're able to do that. They measure the momentum of the particle and the specific ionization per unit length. And they conclude that the penetrating component of the cosmic rays is a particle with about 130 times the mass of the electron. This is not the most accurate measurement. We would say now that they were low. They're only about 2/3 of the modern value for this particle, and which particle it is we will discuss on the further slides. But it's pretty good, and definitely good enough to know that this is not an electron. It's certainly not an electron. And so what they were asking themselves is, have we identified the Yukawa particle? And what might be a way in which the Yukawa particles, that is the particle which is hypothesized to bind the nucleus together, how might that be distinguished from other quote unquote mesons, meaning medium energy particles or medium mass particles, which might also be in the cosmic rays. A pair of theoreticians, Tamanaga and Araki in Japan in 1940, made a study of the interaction of the Yukawa particles with matter and hypothesized that the interaction of positive and negatively charged Yukawa particles with matter should be rather different. So both the positively and negatively charged versions of the Yukawa particle should interact with nuclei in material via the strong force. After all, they're supposed to be the force carriers of the strong force. But there's some differences in the phenomenology of how this takes place. The negative ones can be attracted into very small radius atomic orbits, basically acting like a very heavy electron for as long as they live. And that radius is actually about the same as the radius of the nucleus itself. So the idea is they kind of just fall onto the nucleus. They're essentially absorbed into the nucleus. But the positively charged version of the particle would feel a strong Coulomb repulsion from the positively charged nucleus and come to rest in the material far from any nuclei and then decay in free space. So doing an experiment to figure this out would involve the ability to distinguish both the particle coming into your experiment and then decaying later. If we want to see the positively charged mesons decaying, we need to be able to somehow trigger on the track coming into the experiment and then wait for it to decay and see that decay particle coming out. And the way that we do that is through what we would call a delayed coincidence. And this is an example building off of Rossi's circuit from a few slides ago. So what we have here are two tubes, each connected to their own triode. So it's the same kind of idea as before, where these things are only going to allow current to pass through when this grid becomes charged by the current pulse coming from the Geiger tube. And then we basically connect each of these two things to an RC circuit where we've chosen different values of the resistance and capacitance in order to shape the current pulse coming out of these two legs of the coincidence differently. So like, let's say that we want to detect something which fires T1 and then some time goes by and then it fires T2. What we'd want to do is choose like resistance and capacitance in this leg of the circuit to draw that T1 pulse out over a long time, right? So the positively charged mesons that we see, we think that they have a decay time of about 2 microseconds from other experiments. So one wants to stretch out the signal from T1 for at least 2 microseconds so that if T2 arrives during that window, the sum of the two will be enough to fire this tube at T3 and cause a current pulse on our recorder. So the name of the game is basically to vary the electronic components in these shaping circuits in order to increase your acceptance for a certain amount of delay between T1 and T2. Of course, here we're talking about decays of particles that follow an exponential distribution. So the decay time is not always identical, but there is a characteristic decay time. And we want to make our experiment sensitive to that characteristic decay time and not other random coincidences. Now they can be random in time as well as in space. And we do that by choosing these shaping circuits. So what I can do with this arrangement is something called the CPP experiment. So I have variable delay lines that I can use to zero in on 2 signals. The incoming particle, if it's the positive meson, the positive Yukawa particle, it should come to rest in my absorber and then decay later after about 2 microseconds. I tune these delays so that if I get a track coming in, then nothing for 2 microseconds, then a decay, I will fire this thing. And what these guys, Conversi, Pancini, and Piccioni are doing in the years 1943 to 47 is trying to implement this to determine if the mesons seen in cosmic rays are the Yukawa particle or not. They did this experiment in Rome during World War II. There's like tanks and stuff like driving around the physics building probably while they were doing this experiment. They say in their paper, difficult conditions. I think it really was truly very difficult. Luis Alvarez called this the first modern high energy physics experiment. And that's because of this kind of clever combination of analyzing magnets, coincidences between different electronic detectors like arrayed in space around the target, and then using the digital logic between these different things in order to try to emphasize your signal and suppress the background. So just to sort of describe how this works, I'll ask you on the homework to go into a little more detail, but the basic idea is the following. These plates on either side here are magnetized, and by choosing the direction that the current flows around these magnets, you can either sweep negatively charged particles towards your target or sweep positively charged particles towards the target. So by reversing the polarity of these magnets, you can reverse the sign of the particles that tend to come through here. And you accomplish that by having the coincidence of A and B. So only particles of a certain combination of charge and momentum will have the right curvature moving through this magnet to fire A and B in coincidence. Then you have the absorber here. So if it's the Yukawa particle, what should happen is that at least some of these things which fire A and B in coincidence should then come to rest in the absorber and then decay later. So these counters C on the bottom of the absorber are looking for the decay products of the positive meson with a variable delay between 1.0 and 4.5 microseconds. Remember, we said that they thought the lifetime of the positive meson was about 2 microseconds. And then there's these veto counters at D here and D here, which are basically there to screen out any showers, right? If a shower initiates at the top of this whole thing, it could like fire all these different things at once, but that's not what we want. We want only the events where a single particle comes in, fires A and B, but not D and not D here, and then comes to a rest in the absorber and upon decay fires C. And then by tuning this delay line, one can measure how the rate of coincidence changes and zero in on what the lifetime of the particles inside of this absorber is. See if it's consistent with the phenomenology of the decay that Tamanaga and Araki had calculated in their study. So here is a summary of what they saw. So they can turn the polarity of the magnet to select positive or negative particles. When they do that with an iron absorber, they see the positive mesons decaying, which is consistent with what Tamanagi and Araka would have predicted. But the negative particles, the decay rate is basically 0. Weird. They take the target out and they see no decays. That's consistent with Tamanaga and Araki, because if there's no target, there's nowhere for the mesons to come to rest. And so we shouldn't see the delayed decay. What's really weird is what happens if they put a carbon target in. So if they put a carbon target in, they see decays of both positive and negative mesons, whereas for iron, they see only an appreciable rate of positive decays. So this is very weird, and it doesn't really confirm or deny the predictions of Tamanaga and Araki, but it shows that there's something actually different about the interactions of the positive and negative particles beyond the difference that Tamanaga and Araki predicted. In further experiments, they take out iron and replace it with all different kinds of metals, and they find that magnesium, which is a Z of 12, which is in between carbon and iron, about half of the negative mesons decay with magnesium. And then as you go up, the difference between positive and negative is more, and as you go down from magnesium, the difference is less. And none of this was predicted by Tamanaga and Araki. So the picture must be more complicated, and we're going to need a different type of detector to resolve the situation. Unfortunately, we don't have time here today to say what that different detector is. So that is where we will pick up at the start of the next lecture. So we have a couple of minutes left in case there are any questions or anything you guys want to discuss. Go ahead and raise your hands on Zoom if you have a question. All right, I guess there are none, in which case I will say thank you to you guys. I remind you that I'll be posting problem set 1 on the website tomorrow with turn-in instructions to follow. And just to remind you of what I said in the first lecture, I really encourage you to attempt the problem set even if you're just auditing the course, because we'll spend a little bit of time discussing some of the answers to the questions in the lectures, and I think it will just serve as a useful check to see if you've internalized the material. But with that, I'll say goodbye until next week's lecture, and I will be holding my office hours at the time and place that you can find on the agenda page in case you have any questions that you would rather ask me there. So take care, everybody, and I will see you next time.
Thank you.
Thank you. Bye-bye.
Thank you.